Okay, so
Fine.
the next speaker is Dlyaver, will be presenting Streamlining HDF5's AI workloads benchmarking, which sounds very interesting. Okay, so.
Hi everyone. My name is Dlyaver Djebarov, and I'm a computer science master student at RWTH Aachen. And today I'd like to present our work titled Streamlining HDF5's AI workloads benchmarking. So let's start. I guess it's not secret, and everyone mentioned that artificial intelligence is being rapidly adopted across science and industry, introducing new computational patterns that traditional HPC systems weren't originally designed for. One of the main challenges is I/O. AI workloads place increasing demands on I/O systems, often exposing performance bottlenecks. Despite this growing need, there are still very few benchmarks that capture the I/O behavior of AI applications. Most available tools focus on traditional HPC workloads and fail to reflect modern AI-driven patterns. Since HPC systems are shared between both AI and traditional applications, tuning them requires a unified view. We need benchmarks that evaluate both types of workloads in a consistent context. To address this problem, we extended H5 bench with realistic AI workloads, helping researchers to better understand and optimize I/O performance across diverse scenarios. But what is H5 bench? Let's start with that. H5 bench is a latest suite of parallel I/O benchmarks for HDF5. The big advantage of this suite is that it supports various HDF5-based I/O workloads, such as AMR, which stands for Adaptive Mesh Refinement OpenPMD. It's a standard for exchanging particle and mesh-based data from scientific simulations and experiments. And for example, E3SM-IO, which is E3SM Climate Simulation Model IO kernel. So therefore, we can say that our extension could bring broader pattern support to H5 bench. Okay, now we have a problem. We need to get somewhere I/O patterns for AI workloads, which are typical for AI workloads. And for this purpose, we are using the DLIO benchmark. So the DLIO benchmark is a widely recognized MLPerf Storage benchmark kernel. It was developed to emulate I/O patterns and behaviors typical of deep learning applications. So what's good? DLIO enables predictable and reproducible I/O behavior, unlike real ML apps, which can be unpredictable and unreproducible, unfortunately. It also supports other common AI data formats, such as TF record and NPZ, and not only HDF5, which is also in our interests. Research interest. But the big disadvantage of this benchmark is that it requires the installation of ML library dependencies, like, for example, a lot of dependencies for PyTorch and TensorFlow libraries. So we emulated I/O patterns. We got emulated I/O patterns from DLIO benchmark, and we extracted them using LockVFD. LockVFD is a virtual file driver designed to capture metrics and access activity for HDF5 files. As you can see here, the output consists of multiple lines. Please try not to read them all. As you can see here, each line consists of a range of access bytes, the number of bytes, type of accessed memory, and the type of performed operation. In this small example, we see a log produced by LockVFD in which we are open an HDF file, which is 256 megabits, which has a size 256 megabits. As you can see here, we allocate some memory for that. And we're trying to read the first 64 bytes from this file, as you can see here, for example. So after we get some patterns, we start our implementation. In our implementation of extension, our workflow consists of data generation, training, and evaluation processes. The calculations in our extension are emulated by sleep function and can be fine-tuned using configuration file. Multiprocessing, which is an essential part of AI workloads, is implemented using thread pool principle, where each thread is created using a fork. Why are we using fork function? Because this is exactly the way PyTorch and TensorFlow are creating new threads. After we implement our extension, we need some experimental setup, some experiments, and sanity check. So for our experiments, we run on QX23. It's a supercomputer cluster at RWTH Aachen University. It runs on Intel Xeon Sapphire Rapid CPUs. It has a fat tree topology utilizing the InfiniBand network with a bandwidth up to 25 gigabytes per second. I have two file systems on our cluster. These are Lustre and Beyond. Lustre file system is a RAID 0 type file system with 16 megabyte stripe size and stripe count from 1 to 16 that depends on the file size. It also should be mentioned that Lustre is a shared storage resource. That means that multiple users can use one Lustre node at the same time. Beyond is also a RAID 0 type file system with 512 kilobytes chunk size. It has 4 storage targets and 1 storage pool. Each node of Beyond file system, each Beyond node has a 1.4 terabyte SSD and it's used exclusively. That means that only one user can use one node at a time. So, firstly, we compare the access patterns produced by the benchmark and the original DLIO code with the same settings using log_vfd. Please don't read the right-hand side of the raw log. It's just an example, just a demonstration of what we have. We had a lot of files, a lot of log files, which consist of thousands, maybe 10,000s of lines. As you can see here, we made some summary from these lines and got a lot of tables like that, where we can see that the number of calls in both files with the same configuration was always the same. And what is really important, that the logs are the same up to permutation. That means that our extension is doing the same thing as DLIO benchmark from the view of HDF5 files. Secondly, we conduct a runtime and pattern analysis of DLIO with PyTorch and TensorFlow and our extension. The left-hand side, as you can see, is DFTracer trace visualization. DFTracer is such a program, such a tracer that visualize traces produced by DLIO benchmark. We can see here a lot of rectangles. Every rectangle stands for a function call. We get this data and extracted from them the right-hand side. We extracted from the H5Z read calls. As you can see, they are represented as green bars. Every green bar is one H5Z read call, and every width of every bar stands for the durability of this call. And as you can see, visual patterns vary across frameworks. The underlying HDF5 I/O behavior remains consistent because the number, for example, the number of calls is the same. Our extension isolates pure HDF5 patterns enabling clean and backend agnostic analysis. After that, we got some more experiments. For example, here we were trying to compare HDF5 read operation runtime of our extension and DLIO PyTorch backend. We used only one process to make experiment as clean as possible. 8 training files and 4 samples per file. That gives us, as you can see on XX, 32 or HDF5 read operations. We used LC beyond FS. As I said, it's used always in exclusive mode. So we want to make experiments clear as much as possible. As you can see here, I/O times varying while consistently maintaining an overall pattern on over average. That means, again, that from the view of HDF5 files, our extension behaves equally as DLIO benchmark. So we succeed in extracting patterns. Then we did some scaling tests because we are doing HPC. Here we compare Lustre and beyond. We run H5 bench extension with 1 to 32 nodes with 24 processes for each node. In Lustre and beyond with 384 gigabytes of data for training phase and 96 gigabytes for evaluation phase. As you can see here, there are some metrics like raw read rate and observable read rate. These metrics are provided by H5 bench, and raw read rate is equal to total read size divided by the total time performing H5D read, and observable read rate equals to total read size divided by the total time to complete the benchmark run. Yes, as you can see here, our extension scales well. That's a good sign. The Beyond file system in our cluster achieves a higher read rate performance than our Lustre file system. Our H5 batch extension runs indicate the need for further optimization of the Lustre file system, particularly as it's mainly used for more traditional HPC workloads. But the main reason why Beyond is faster is because it uses SSDs on our compute nodes. Yeah, then we got more experiments. Let's consider them. Let's consider first the Beyond experiments. Here we used only one node. One node with 1 up to 64 processes per node. As you can see, the read rate per rank declines as the number of processes increase. This behavior is expected as the node becomes fully utilized and the peak network bandwidth, which you can see here, is reached with 64 processes. Additionally, the overall read rate reaches its higher point with the maximum number of processes in our test. Possibly, you can observe here fabric bandwidth degradation, and that's because the measurement intervals of our measurement tool, which is called performance monitor, are very small. We find some kind of bug in our cluster, but now it's repaired. Yes. Let's go to the next scaling test on a Lustre file system. Here we were testing multiple nodes from 24 to 768 processes. When testing the Lustre file system at a larger scale, we observed that the workload scales as the number of processes increase. You can see it here or here. Notably, there is a jump in the read rate per rank between 96 and 192 processes, which can be attributed to node and network effects. Yes, here we can compare both results. And we're going slowly to the conclusion. The conclusion is our extension, H5 batch extension successfully mimics HDF5 code patterns from real AI workloads in DLIO. Especially, striping the Python environment confirmed that underlying HDF5 codes remain consistent, underscoring the need to isolate I/O from ML library effects. Our scaling tests, as you can see, demonstrate that the extended benchmark behaves as expected for both AI and traditional HPC workloads. It's also planned to be integrated into H5 Bench version 1.6 soon, I guess in next month, if everything works as it should. Our extension also eliminates the need to install machine learning libraries dependencies for HDF5 focused performance tuning. And what is really important, our H5 extension supports researcher in evaluating system performance in AI context, but also helps sysadmins to focus on tuning HDF5 for AI workloads. What are we going to do in the future? In the future, we aim to analyze the impact of network and data transfer strategies in various ML libraries. Since it is our research focus, we plan to deepen our understanding of I/O impact of various file formats like TF record and NPZ compared to traditional HPC file formats and I/O strategies. Additionally, we want to integrate checkpoint write operations in HDF5, which may become relevant for future AI applications because checkpoint operations are essentially in modern AI workloads since the models are getting bigger and bigger. Also, the including workloads from variety of applications beyond DLIO will provide deeper insights into system performance across a broader range of AI and HPC workloads. So our plan is to integrate other benchmarks like DLIO to get a deeper insight. Thank you for your attention. If you have any question, you can write me an email or read my bachelor thesis. There you can find a lot of details on the implementation and more experiments. Here you can find also a QR code. If you scan it, you will see the current status of our extension and the status of pull request to H5 Bench repository. So again, thank you for your attention. If you have any questions, I will answer them.
Okay, let's first have a round of applause for the speaker. And yeah, do we have any questions? Yeah, we have a question.
Oh, fine.
Hello, thanks for the talk. Yeah, you were comparing like the performance of these two different file systems, and the case where you were writing onto like a local SSD was faster. I was curious, like, is that beyond file system? Like, does it then sort of is it stored in some way that's then accessible from other nodes as well, or is that like purely stored accessible on one node?
That's a good question. In our QX23 system, beyond nodes are accessed separately from Lustre nodes. Yes, as you said, our beyond nodes they have 1.4 SSDs, which certainly make things faster.
So that data is like just local to the node that you store it on. It's not then accessible for the rest of the cluster. Or is beyond?
I guess it is.
Extra behind the scenes.
I guess it is, but in our experiments, all of them were located local.
Okay,
Wait.
Thanks.
Any more questions? Okay, I'll check online. Yeah, online. Okay, I think that with that we can thank speaker again